Good afternoon. Good afternoon. Hope all is well. Hope everyone doing all right. So still got a few people connecting with the audio. So I'm giving them a chance to do so. Till then, we are getting we're gonna pick up where we left off at 6.2. And we're right here in establishing standard 52 card deck. So let me see, make sure everybody's in here. Looks like we are good. Okay. So once again, good afternoon. Hope everybody's doing great. Everybody's all right. So we're in 6.2 still, and we're at the point right now we want to establish the standard 52 card deck, just in case you've never played with cards before, or you don't remember what we call what and everything like that. So here we have that, the standard 52 card deck. Standard means that there are no jokers. In the deck, there are 4 suits: spades, clubs, hearts, diamonds. We have 2 black suits, which are the spades and clubs, 2 red suits, hearts and diamonds, 13 cards each suit. So 13 times 4 gives me my 52 back. 3 are face cards, 10 are regular cards or non-face cards. So the face cards are your king, queen, and jack. Regular cards, ace, and the numbers 2 through 10. So your ace is not a face. All right, anybody still copying this page? Everybody good? All right. So here we are. If we draw one card from a standard deck, what's the probability that it is a spade? So if you remember when we talked about probability last class, whenever you're dealing with your probability, you want to know your sample space, the number of your sample space first. In other words, what's the total number of all possible outcomes? So in this case, it's going to be 52. So the number of our sample space is 52. That's the total number of cards to choose from. Then we need the total number of cards or total number in our event. Our event is spades, picking a spade. So there are 13 spades in the deck. So the total number of spades, 13. And once you have those two numbers, you essentially have the answer, because what you would do is take the number of spades over the number in your sample space, that's 13 or 52. And then from there, it will reduce down to 1 over 4. All right, questions? All right, scrolling up. Relative frequency method of calculating probability. So you would take the number of times that A occurred, the event A occurred, and place over total number of observations. So it's very similar to the theoretical probability calculation, just the wording is a little different. All right. So we have geological records indicate that a river has crested above a particular high flood level 4 times in the past 2,000 years. What is the relative frequency probability that the river will crest above the high flood level next year? Give you a chance to write that down. All right, scrolling up. So all we're going to do is take the number of years with the flood, which was 4, and then the total number of years that we are observing. In this case, is 2,000. So 4 out of the 2,000 years is when it flooded. So we got a 1 out of 500 chance of catching a flood next year. And that's after you reduce both top and bottom by 4. All right, any questions? Everybody okay? All right, can I scroll up? All right. So we have our 3 approaches to finding probability. We've talked about 2 of them already. The third we'll see in a second. It doesn't really call for any calculation. We have theoretical probability. It's based on the assumption that all outcomes are equally likely. It is determined by dividing the number of ways of an event can occur by the total number of possible outcomes. Then we have relative frequency probability, which is based on observational experiments. It is the relative frequency of the event in interest. And then the last one, subjective probability. It is an estimate based on experience or intuition. All right, scrolling up. All right, so here's just an example emphasizing the difference between the 3 ways to find probability. So it says identify the method that resulted in the following statements. I'm certain that you'll be happy with your new car. Based on housing data, the chance that someone will move to a new residence during the coming year is about 1 in 8. And then the chance of rolling a 7 with a 12-sided die is 1 out of 12. So I'll give you a chance to write that down as well, and then we'll look at them. All right. So the first one, I'm certain that you'll be happy with your new car. So get the word certain is actually a probability word. Remember, 100% is considered certain or certainty. Impossible, 0%. So when you use certain words, they are probability or statements relating to probability. So I'm certain that you'll be happy with your new car. Now, in this case, it's just based on this person's experience. There's no data or anything, or even any numbers mentioned. So this one would be subjective probability, just making a statement based on experience or intuition. The next one, based on housing data, the chance that someone will move to to a new residence during the coming years about 1 in 8. So it says based on the housing data. This one is based on observations or experiments. Is relative frequency, and so that's going to be relative frequency probability. And then what sets that one apart from the theoretical is that the chance of rolling a 7 with a 12-sided die is 1 out of 12. It's letting you know that there's an assumption, not an assumption, that each one of these observations are equally likely, or each one of the probabilities are equally likely. And that's what your theoretical probability is based on. Being able to calculate your probability with the idea that what you're calculating has the equal chance of happening. Questions on either one of those three? All right, let's scroll up. So now we're looking at the complement of an event. It's the probability of an event not occurring, or another way of looking at it is consider all of the outcomes in the sample space that is not the event that you're dealing with, or that an event is not. All right. Notation. Let's say if we call the A, capital A, let that represent event A, then A with a bar over it is going to represent your complement. That's not event A. So notice I wrote that this book represents your complement that way. You can go, if you go, whether it be Google or whatever the case may be, and look up complement, you can see different ways of representing the complement. This is how this book represents the complement. It's actually the first time I've seen it represented with a bar over it, but that's how your book represents the complement of your event. All right. Calculating the complement. If I want to know the probability of not A or the probability of the complement, but I know the probability of my event, I can subtract it from 1, and that'll give me my complement. Or if I know the probability of the event, I mean, or if I know the probability of the complement and I want to find the probability of the event, I can subtract that from 1, and that'll give me probability of my event. Or finally, if I were to add the probability of my event and the probability of not my event, they will add together to give us 1. Notice that all 3 of these are the same formula, just to manipulate it according to what it is that you're trying to calculate or find. All right, scrolling up. All right, so in a study of checkout scanning systems, samples of purchases were used to compare the scanned prices to the posted prices. And it says see table. So we have a table down here. Based on the data, what is the probability that a regular priced item had a scanning error? All right, very good. Scrolling up. This is the chart, the table. You have undercharge, overcharge, correct price. Then up top, you have regular price items, advertised special items. You got 2015, 384, 729, 364. All right, can I scroll up? We're done with black. All right. So what is the probability that the regular priced item had a scanning error? So when we look at the regular price item, we're just looking at this column right here. And if we're dealing with probability, once again, we need to figure out what is our sample space. So in other words, what's the total number of regularly priced items that we're choosing from in this case? And so we just add in the 20, the 15, and the 384, and that gives us 419. So there's a couple of ways that we can find this answer. I'm going to use the complement way since this is the complement section. So the number of correctly priced items is 384. So the probability of getting the item that was priced correctly is 384 over the 419, which is 0.9165. And don't forget math level, let you know what decimal place they want from you, whether it's 3 or 4. Any problems so far? All right, so remember we're looking for something that was not correctly priced. We're looking for a scanning error. So if 384 out of the 419 was correctly priced, that means to find what was not correctly priced or what ended up having a scanning error, whether it was overcharged or undercharged. We can subtract that 0.9165 from 1, and it gives us 0.0835. Any questions? Any questions? All right, can I scroll up? All right. I think that's the last thing out of this section. Probability distributions. That's the complete set of probability results for events. And it represents the probability of all possible events. All right. So to make the probability distribution, we have a couple of steps. Should help you to do so. So first, we want to list all possible outcomes. And now you need a table or figure to help you out there. Identify the outcomes that represent the same event. Find the probability of each event. And then make a table in which one column lists each event and another column lists each probability. And then notice the last statement in red is that the sum of all probabilities must equal to 1. All right, so let's try to put this to work. It says make a probability distribution for the number of heads that occur when three coins are tossed simultaneously. All right, so very similar to the problem with the two dice. If we want to know the total number of possible outcomes, what you do is multiply the number of options for each one of the die. You know, we had a die that had 6 spaces and another die had 6 spaces. So 6 times 6 gave you 36 possible outcomes. So the same thing happens here. We have 3 coins. Each one of them have 2 options. So 2 times 2 times 2, that gives you 8 possible outcomes. And so when we go about listing our outcomes, we have to make sure that we come up with 8 of them, 8 different ones. All right. So you would just make sure you have a systematic way of labeling it out. And then if you get stuck, like I said, that's your check right there. If you don't have 8 different outcomes, then somewhere you miss one, or 2 or whatever it is that you're missing. So you're talking about throwing up 3 coins and all of them laying heads. Then we're looking at tails, heads, heads. Then we're looking at tails, tails, heads, tails, 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 heads, tails, heads, heads, tails, tails, heads, heads, tails, and then tails, heads, tails. All right. So in the green, what you want to do is go ahead and mark what you have of each outcome. So we're talking about flipping these coins and determining the outcomes in terms of heads. So we're looking at the outcome or outcomes that had no heads, 1 head, 2 heads, and then 3 heads. So that's what we're looking at right here. And so when I go and examine my outcomes, there was one time that there was no heads at all. That's tails, tails, tails. Then 3 times that 1 head appeared, 3 times that 2 heads appeared, and then we had one occurrence in which all 3 coins landed heads up. And once again, don't forget that should add up to give you 8. 1 plus 3 plus 3 plus 1. All right, and then over here is our probability distribution. We have the number of heads, 0, 1, 2, 3, and then the probability is 1 out of 8 chance of getting 0 heads, 3 out of 8 chance to get 1, 3 out of 8 chance to get 2, and then 1 out of 8 chance to get 3 heads. Any questions? Any questions? Everybody good? All right. So last class, we were able to start 6-3 Got through one or two examples and that was it. So we'll do the same here. Looking at the law of large numbers. So the law of large numbers applies to a process for which the probability of an event A is the probability of A, P of A, and the results of the repeated trials do not depend on results of earlier trials. So in other words, they're independent. All right. It states that the process is repeated through many trials. The proportion of the trials in which event A occurs will be close to the probability of A. All right. In the last statement on law of large numbers, the larger the number of trials, the closer the proportion should be to the probability of A. All right, scrolling up, a roulette wheel has 38 numbers, 18 black numbers, 18 red numbers with 0 and double zero in green. Assume all has equal probabilities. What is the probability of getting a red number on any spin? All right, so A is just really a regular probability question, um, similar to what we've done, in the previous section. First thing we need to establish the total number of outcomes. So there are 18 black, 18 red, and 0 and double zero, so that's 38. But also they gave us 38 right here. So total number of outcomes is 38, or total number of numbers to choose from is 38. And then total number of reds. We want to know what's the probability of getting a red number on any spin. So total number of red numbers will be 18. So then that's 18 divided by 38, which is 0.474. Any problems with that? So B, if patrons at the casino spin the wheel 100,000 times, how many times in a red number is a red number expected to result? All right, so according to the law of large numbers, the more and more the game is played, the closer the proportion will get to 0.474. So our conclusion, in 100,000 tries, the wheel should come up. I said the wheel. Yeah, I was right. The wheel should come up red. There you go. The wheel should come up red close to 47.4% of the time. You know that 47.4 is coming from here as a percentage. And or about 400, 4,700, 400 times, 47,400 times. I can get my words right today. 47,400 times. And that comes from taking that 0.474 and multiplying it times to 100,000. All right, questions, any questions? Everybody good? So I believe this was the last one. Yep, for the last class. You know, of course, when I'm writing it, write a little slow, so they're waiting on me. So this is where we'll stop today. Next class we'll pick back up. We'll still be in 6.3. We're gonna finish out 6.3 and probably touch on 6.4 as well. Before we go, did anybody have any questions on anything? Oh, somebody in the chat. The test review for which one? What test?
Is that coming up next week? The test?
No.
Okay, so it's next week because we have
All right, so chapter 5 and 6. No, I'll look to pick make it so because let me see. I think this doesn't end until 6. Let me see.
The last one is 6'5".
6:5. Yeah. Okay. Yeah. So I'll be posting it soon. I haven't made it yet. So as
Okay.
far as the test review, it hasn't been made yet, but I could try to get it to you, get it posted sometime this weekend.
The test. Okay.
Yeah, what one of your other classmates was asking, he had
Okay.
a direct quote, direct question.
Okay.
Mhm.
Yeah, I gotta get some assignments done.
Yep, not a problem, not a problem. All right. So any other questions before we close out? Then make sure we're good. All right. So like your classmates, alluded to, this chapter 6 ends in 6:5. So got a couple more sections to go to close it out. Um, but hopefully by next week we can close out chapter 6, and then the test will be posted in Math Lab for you guys to do. It won't be over Zoom like it was like the last test. All right. So you guys have a great weekend. Be safe, and I will see you next class.